Okay, welcome everyone to another live session for the online class, and apologies as we start for technical problems today. It's a snafu that we'd never seen before, getting the YouTube live session going. It sort of canceled itself after a few seconds and sort of stranded people who were looking at that stream. Anyway, if those of you persistent enough or clever enough to figure out where we moved to are with us now, and we have email questions, so we'll go right ahead. Maybe this is just a sign of the times, the end of days. You know, those of you who've read apocalypse fiction like The Road by Cormac McCarthy know what it's like, the end of days. So we're just seeing little inklings of the end of days. And actually, to start, I'm going to ask and answer my own first question because it was over 3 weeks since our last live session, and you may have seen the news story about these few people who were down in the Grand Canyon rafting for about 3.5 weeks, and they had no cell phone coverage, no reception, they weren't online in any way, and they essentially came out of their trip a few days ago to a totally different world. And it was a totally different world last time we had a live session. So the first question that I'm going to ask and answer is, how has the coronavirus affected science in general and astronomy in particular so far? And at first glance, you might think that's not an obvious question to ask. This is a health issue, a profound human health issue. What has it got to do with science and research? Well, actually, I just wrote an article for The Conversation. That's an online magazine. If you just go to The Conversation and search my name or coronavirus, you'll see tons of articles about that. And I was asked to do a little article on the effect of this pandemic on research. And after going online and researching it, there's a lot of impact on research in general. It perhaps more affects the life sciences, because at roughly 250 research-intensive universities around the country, if you multiply that number by about 10 or 12 science departments, and each department a handful of labs, you're talking about in excess of 10,000 labs that are largely shut down now because universities are either closed, the students have all gone away, social isolation, no more than 4 people are allowed to meet at the University of Arizona. And so lab work is really shut down completely. Astronomy is not immune from this. Just within the last 24 hours, the last of our big telescopes has been closed temporarily. The Large Binocular Telescope on Mount Graham was closed. A couple of days ago, Chile closed its borders, and our telescopes down there, the Magellan telescopes in Chile, were closed. And our small telescopes in Arizona have also been closed, and that largely is a sort of staffing issue, as more people are sort of temporarily furloughed or working remotely. We just don't have the people on site to maintain these telescopes. And this is just what the part I know. I haven't heard from all my colleagues. So basically, research is really being impacted by this across all sciences, and in astronomy, we're seeing it very directly. Just observations, are starting to shut down. I would guess, and I have colleagues that I've confirmed this with, the sector of science that's probably least affected by the coronavirus is big science in the physical sciences. So Large Hadron Collider, huge accelerators and physics experiments are largely run remotely by research groups, thousands strong, dispersed around the globe. And they actually have very few staff required to keep them running in a minimal operation. So these projects can keep going. At the Hubble Space Telescope, another good example, astronomers don't actually control the telescope in real time. There's a staff that run the telescope. They may have a minimal staff, but those functions of the Hubble are largely automated. They're run by sort of AI software to schedule it and control it and look for problems. So I suspect these large facilities are continuing pretty much uninterrupted. But there is an impact, pales, of course, in importance compared to the health impact on people all around the world. But for anyone who is wondering, yes, it is hitting research indeed. Ready for the next question.
Thank you, Chris, and thank you all for your patience. And to those of you who have made it over here, thanks for joining us on this new session. The next question is from Javier, who posted a question in our last live session that said, I read an article that talked about open and closed universes and changing things about the Planck tension. Can you talk about how the shape of the universe is determined and what is Planck tension?
To deal with the last part first, I'm not entirely sure. That's not a standard physics term, actually. But the Planck era, the Planck scale, is the scale that applies to the universe when all the forces of nature are unified, which is a tiny time after the Big Bang, a Planck time, in fact, as it's defined, 10 to the minus 43, 1 over 10 with 43 zeros after its seconds after the instant of the Big Bang. So I don't know what the adjective tension applies to in this context, but the Planck tension could either refer to the tension of not really having a theory or a sort of satisfactory theory that unifies gravity in a quantum sense that lets us understand this era, or the tension that applies in a more physics-minded sense in between the forces of nature in the very early iotas of the universe. As far as open and closed, well, the conditions that lead to open or closed were essentially baked into the universe at the beginning. So they were initial conditions or boundary conditions of the Big Bang, because the curvature of the universe is determined by its contents, its energy, mass energy contents, and its dynamical history is governed by those contents, which are largely dark matter and dark energy. And as we measure those entities today, almost 14 billion years after the Big Bang, the dark energy is ascendant, it's 3 times larger than the dark matter, and so the universe is in an accelerating state of expansion. And that means that geometrically, in terms of general relativity, it's flat, and possibly even slightly hyperbolic with negative curvature. So it is definitely not closed. So the positive curvature, closed or oscillating universes that were in vogue in the 70s and before are definitely off the table. That's not the universe we live in. We measure the spatial geometry of the universe using the way light travels from the epoch of the microwave background radiation, 400,000 years after the Big Bang, all the way till now. So these are giant optics experiments using microwaves through the whole vastness of the universe, and they really do show that the universe is very close to spatially flat. So measurements with the cosmic microwave background, CMB, establish it to be flat to less than 1%. So really no spatial curvature at all. And that's the basis of us saying that we live in an open universe, because a flat geometric universe will expand forever. Ready for the next question?
Thank you, Chris. So the next question is from D. Zach, who is on with us live right now, made it over. And they would like to know, how many objects orbit the Earth apart from the moon?
Tens of thousands. It depends on what size you go down to. If you're just talking about satellites, regular telecommunication satellites, living or dead, the dead ones are designed, they're designed to deorbit by losing altitude through drag in the very thin upper atmosphere and then gradually burning up in the atmosphere or falling into the ocean or sometimes onto the land. Or they just stay there as dead shells if they're in a high Earth orbit. So the number of substantial telecommunications satellites is several hundred. The number of satellites of any kind, including CubeSats and nanosats and more recent technologies that let satellites be made quite small, is several thousand. But the amount of space debris in Earth orbit is vast. I mean, that's millions of pieces of debris if you're talking about going down to the size of, say, a marble or a small rock. And those pieces of debris, the many millions of them, are actually the things that are very damaging, because anything larger pretty much than the head of a pin traveling at 50 or 60 or 70,000 miles an hour that hit the International Space Station would puncture its skin, carries so much kinetic energy. So the objects that orbit the Earth are mostly not very large, but they are extremely dangerous because of their high speed. And that number is, of course, increasing over time. SpaceX is just alone as one company is planning to end up with a mega constellation of over 30,000, I think the number is 32,000 satellites, which it will use for delivering internet around the world. So there are new companies that are on their own doubling or trebling the number of substantial sized satellites in Earth orbit. So this number is going up, to the concern of astronomers who worry about light pollution, about interference with their deep optical observations of the universe.
Thank you, Chris. So at this point, about 30 people have made it over. So thank you very much for sticking it out and trying to find us. The next question is going to be from email. Gitanjali would like to know if black holes have indefinite lifespans, or do they eventually fizzle out? Does a black hole need to keep consuming matter to sustain itself?
Well, they do have lifetimes, because even if they are able to accrete matter, eventually they will exhaust the matter available to them. And so in the end, the Hawking radiation, which amounts to the evaporation of a black hole very slowly, will cause it to disappear. So early in a black hole's lifetime, and for the most part of the history of the universe, black holes have essentially been growing. That's especially true of the large black holes at the center of galaxies. They've been growing steadily as galaxies merge and become bigger themselves by mergers and acquisitions, so the black holes within them also merge and grow in mass. In addition, the center of a galaxy is a region very rich with stars and gas and dust, and so those black holes have plenty of material to eat, and so they grow steadily. The rate is quite small, even for a hefty galaxy with a hefty black hole of, say, a few 100 million times the mass of the sun. The increase of mass rate, or the mass accretion rate, is only about one or a couple of solar masses per year. Well, that sounds small, but of course, in a billion years, that's a billion times the mass of the sun accreted. So the black hole could easily, a big black hole could double in mass in about a billion years. So they are growing. However, the countervailing trend there is towards evaporation. So in the big picture of the history of the universe, they've been growing. They will continue to grow, but eventually the material to grow with will be lost, because stars, all the other stars around the black hole, will become stellar remnants, white dwarfs for the most part, and the gas will disperse or diffuse or already have been consumed, and so there's no material for the black hole to accrete. The same is true of black holes in the center of galaxies, and also on very long time scales of many trillions of years, galaxies will evaporate. The stars will gradually be flung off or leak off into intergalactic space by dynamical effects. So black holes, large and small, will eventually lose fuel with which to grow in mass. And thereafter, Hawking radiation will be the dominant effect. Now, the timescale for Hawking radiation, which is the evaporation of a black hole by loss of energy or equivalently mass, is an incredibly slow process, about 10 to the power 56 years for a black hole the mass of the sun. And for the most massive black holes in the universe, it's about 10 to the power 98 or 97 years, just a almost unimaginable time. But if that theory is right, I mean, that Hawking idea of evaporation has never been observed, so it is just a hypothesis. It seems to be a good theory, but we don't know. If that's correct, then they are not eternal. They will eventually evaporate.
Thank you, Chris. There are, so the next question is from Dee, who's very interested in planetary science. And the question is there really ice on Mercury?
Yes, this has been a surprise. We've, had a NASA space probe at Mercury recently in the last couple of years. It's been a sort of neglected corner of the solar system. Mars has had a lot of attention. The outer solar system, Jupiter and Saturn, have had attention going back to the 1970s. Mercury Messenger has finally given us a close look at Mercury. And yes, there is ice in the polar regions of Mercury. Obviously, it can't exist in the equatorial regions or the strongly sunlit regions, because the temperature there is 700 or 800 or 900 degrees. But it can exist in shadowed regions. It can also exist in the subsurface soil, because remember, the temperature in the shadowed region of Mercury, the temperature is 450 roughly degrees Fahrenheit below zero. So it's extremely cold. And so if there were water vapor or water molecules, they would be in the frozen form. And the spacecraft is sensitive enough to detect this ice. So it's kind of interesting because it means that if you ever wanted to set up a base on Mercury at the terminator, you know, the boundary between light and dark where the temperature is not crazy for humans to be, there would be ways probably to remotely gather water on which to subsist with a base there. It's an interesting proposition.
Thank you, Chris. The next question is from Achim, who is on with us live, who would like to know, what is your take on some of the articles that I have read lately about stars that are older than the universe?
These kind of stories come up every now and then. There is a tension in cosmology, so let me start by framing that issue, which is how secure is the Big Bang model of the universe and our current measurement of cosmological parameters. So some of the articles you may have seen relate to the controversies over the Hubble constant, the expansion rate of the universe. We can measure it nearby with galaxies nearby. That's something that the Hubble Space Telescope did early on in its history. And we can measure the Hubble constant or the expansion rate at an earlier time using microwave background and distant galaxies and so on. And these two measurements are in conflict, which is to say they're not consistent with this expansion history that we thought the universe had given its dark energy and dark matter. So that's a tension in cosmology. Now, given that we measure dark energy and dark matter, those components which drive the dynamics of the universe since the Big Bang allow you to calculate a pretty accurate age. And so a very important cross-check on cosmology is, do the age of the oldest objects in the universe accord with the age of the universe measured by these direct cosmological measurements, primarily involving the microwave background. And the number is about 13.8 billion years. And the answer, mostly over 10 or 20 years, people have been making these cases and doing these measurements, is yes, they do. All you need to do, however, is to find one star in principle that's older than the universe that contains it, and you have a big problem. So looking at the age of the oldest stars, which typically are in globular clusters in our own galaxy, is an important thing to do, and people have been doing it for a while. And the sort of papers that are coming out which claim a problem are obviously arguing that the stars they see are older than 13.8 billion years. That's a problem. The trouble is these measurements themselves have uncertainties because they're based on models of how stars evolve. So they're not direct observations of a star's age. We simply cannot observe a star's age directly. That's not an observable quantity in astronomy. It only is possible to derive an age based on a measurement of the mass of a star, an understanding of its evolutionary state, and a model of its evolution. And the stars that are used, if they're white dwarfs, they are very simple objects with simple evolution. So this is not a difficult calculation, but it still has some uncertainties. So I'm aware of a couple of papers you're asking about, and I would say at the moment there's no crisis in cosmology. The measurements of old star ages are still uncertain enough, especially in terms of unrecognized systematic errors, which is a classic problem in the history of cosmology. People have underestimated or not recognized systematic errors in their measurements. If we put a little asterisk and say you really have to understand your errors very, very well, then I would say there's no problem. But it's worth watching out for this space because it is one of the ways you check your cosmology.
Thank you very much, Chris. The next question is from Rajarshi, who's on with us live. Could you talk a bit about string theory versus quantum gravity theory, and which you think to be the most correct or the actual case in reality?
I think there's a lot of research on both, a lot of very clever theoretical research. There's not a lot of observational handles to put onto these theories to distinguish between them, and that's frustrating to a lot of physicists and astronomers. So we're still in the realm of pure theory. Which one do you like better? String theory has caused enormous excitement since the early 80s when it was first developed. And it has disappointed some people, and especially in the last 10 years, because it hasn't sort of delivered on its early promise. And that's in part because the calculations are extremely difficult. And also because string theory is not one thing. It's a set of models, actually called M theory, from M for membrane, which are describing different kinds of multidimensional spacetimes. So string theory at the moment has not been tested and proven. It may not even be testable at the level we'd like. And progress in string theory and the fundamental theory has been slower than we might imagine. On the other side is quantum gravity, and quantum gravity is also not one thing. Quantum gravity is a range of physical theories that try and do what Einstein could not do, because Einstein's theory of gravity, general relativity, involve what in mathematics are called manifolds. Manifolds are sort of spaces, curved spaces, or space-times, multidimensional if you like, and they are smooth and continuous. Well, quantized gravity has to accommodate the fact that the space-time may not be continuous and may not be smooth. And so you're going for a different kind of theory. And so its mathematical and physical basis is quite different. It has a smaller number of theorists working on it than string theory. And they have made some interesting progress, and they've made some theories that at the very least can replicate some of the predictions of general relativity. Because if you can't do that, then your theory is a non-starter. You have to at least start by explaining or predicting all the things we actually observe, and then hopefully you predict some new things that we can observe that show your theory to be correct. So quantum gravity hasn't passed that bar, nor has string theory. So at the moment, the jury is out on both of them. And I would say, you know, the number of frontline researchers working on them, the two theories together, two types of theory together, is pretty modest. It's a couple of hundred worldwide. It's very difficult work, and the progress is slow. So it may be a while before we know what the next theory of gravity is.
Thank you, Chris. The next question is from David Bloomfield, who's on with us live, who would like to know if you can explain what coordinate system is used for charting positions and movements of stellar objects. It seems like the moving Earth wouldn't be useful as an origin.
Right. So, whoops, we just got a little echo. Yes, coordinate systems are very important in astronomy. We make our observations from the Earth, and the Earth, of course, is spinning and orbiting the Sun. So those motions have to be understood very well. And essentially, the two fundamental types of time are time kept relative to the Sun, and that's what civil time is. That's how we sort of run our daily lives, because we pay attention to the Sun and day and night. But astronomers actually prefer sidereal time. Sidereal time makes more sense because that's time kept by the stars. And essentially, in simple terms, if you're at an observatory or just standing outside in the night sky, it's the time it takes for a particular star that transits overhead or goes through the meridian to reappear, to cross the meridian one day later. That's a sidereal day. So that's how timekeeping in astronomy works. As far as coordinate systems, astronomers and their telescopes in particular, and some amateur astronomer telescopes too, use equatorial coordinates. And they are, of course, referenced to the spinning Earth. So they're referenced to the projection out from the equator of the Earth off into space, and the projection from the poles of the Earth out into space to a fixed point. Because those are the points, the celestial poles, north and south, about which the stars appear to rotate in the night sky. So that's a natural reference frame for coordinate systems in astronomy. And those coordinate systems, the equatorial coordinate system, is pretty much used by all astronomers. That's how they keep their catalogs of objects. That's how they pass information to other astronomers and observers who may want to observe something at their telescope. And it's a pretty useful coordinate system. Now, it's not a perfect coordinate system because it's not the only motion. As you know, the Earth precesses on its axis. So the spin axis of the Earth is not pointed at a fixed point into the galaxy or into the celestial sphere. It pirouettes with about 26,000 year orbit, and so the pole star, the Polaris, will not be near the North Celestial Pole in a few thousand years. And a few thousand years ago, when people started observing stars carefully, it wasn't the pole star then either. So modern astronomy coordinate systems have to take into account the precession of the equinoxes, or the sort of precession of the Earth as it spins. The timekeeping systems associated with astronomy also have to take into account the Earth's elliptical orbit and the fact that it has a non-uniform motion as it moves around the sun. So there are sort of zeroth order or basic timekeeping and coordinate systems that have to be modulated or adjusted with small but significant corrections throughout the year. The fundamental basis for the timekeeping is, of course, atomic clocks, and there are now atomic clocks of enormous precision. The major observatories actually have their own atomic clocks, so they don't have to depend on anyone else's.
Thank you, Chris. The next question is from Shou Shin, who's on with us live, who would like to know, how far away from Earth would you have to travel for the constellations to stop looking like we know them as seen from the Earth?
Yeah, that's a good question. So it's just to back off to what the constellations are. The constellations are apparent groupings or patterns or asterisms on the sky. And they adhere to the idea that the sky, the night sky, if you just go out there and intuitively, just looks like a two-dimensional surface. It looks like a dome centered on the Earth. But of course, we know, the ancient people really did think the stars were attached to a celestial crystalline sphere. That's what the Greeks thought. We know, of course, that the stars are distributed in three-dimensional space, and so they're at very different distances. So the stars that are next to each other are typically at quite different distances. Now, that's not true always. In some parts of the sky, like in Orion, there are parts of the Orion constellation, when you get down to the fainter stars, that are in the Orion Nebula or near it, near that star-forming region, 1,300 light years away. So they are at the same distance. But the stars, say, in the Big Dipper are all at different distances from each other. So the question then comes, how far would you have to go and change your perspective before you are moving among the stars, or their relative positions and angles as seen from where you are changed enough that they stop being recognizable? And a sort of basic rule of thumb is, if you get more than about a quarter or a third or a half the way to the stars that are in the constellation, then their apparent position on the sky will really start to shift. Their parallax will start to shift relative to the other stars, and the constellations will start to look distorted relative to what they do on the Earth. Of course, once you move to distances where you're between the distances of the stars in those constellations, the constellations disappear entirely, because some of the stars in the constellation that from the Earth were in the same direction of the sky could be on opposite directions as you move out. So the typical distance, to answer that question, of say a third to a quarter the distance to the stars in the constellation for the bright stars in the typical constellations of the night sky, is going to be a third to a quarter of a couple of hundred light years. That's the typical distance for the bright stars, which tend to be giant stars at quite large distances. And so you'd have to go from the Earth of order 50 to 100 light years before the constellations would change substantially. And if you went a couple of hundred or 500 or 1,000 light years, constellations would completely be scrambled and be unrecognizable. They just wouldn't exist.
Thank you very much, Chris. The next question is from Mohammed, who would like to know, if space and time are interlocked and the universe is expanding, shouldn't time be measured with respect to the rate of universe expansion?
Yes, it should. So good question. Space and time are linked, and so time is not an absolute quantity. So the idea of a sort of imperturbable underlying clock that ticks along as the universe expands and gets older is not correct. Time is measured locally with respect to the space that it's coupled to, and its local time. Its local time is subject to gravity too, because we know that clocks run slower in a strong gravitational field. That's a very clear prediction and tested prediction of general relativity. So cosmic time is a tricky quantity. Now, you can approximate some smooth, imperturbable cosmic time if your measurements, your clock, if you like, to say it's a set of radioactive atoms which decay with a particular time scale. That set of atoms are very far from any region of very curved space-time, such as near a black hole, or they're very far from any large concentration of matter, like a black hole or a galaxy or something like that, or even a massive star. So you can still talk about cosmic time in a meaningful way, but it actually is not an absolute quantity. You have to make local calculations of how cosmic time behaves, which do depend on the nature of space locally, and in turn, the nature of space depends on the mass energy content of that part of the universe, because that's what general relativity says.
Thank you very much, Chris. The next question is from one of our live viewers, Oopsa Daisy, who I'm guessing is a pseudonym, would like to know, how certain are we that the speed of light is really constant, and what implications would a potentially non-constant speed of light have regarding astronomical measurements and estimations?
It's pretty well determined that the speed of light is constant, independent of the observer. The first measurement of that was from 1895, the Michelson-Morley experiment, which was an attempt to detect what physicists used to call the ether. The ether was a hypothetical medium that pervaded space with respect to which everything moved and with respect to which light traveled. And so in the Michelson-Morley experiment, they tried to measure the existence of the ether by essentially looking at the timing and arrival of light from astronomical objects as the Earth was in different parts of its orbit. So obviously, in one part of its orbit, the Earth is moving towards some stars in the night sky, and 6 months later, it's moving away from those stars. And in principle, you can make a lab experiment, which they did, a physics experiment 120 years ago, 125 years ago, which was designed to see whether the speed of light from the same star measured 6 months apart as the Earth was moving at different speeds was different, and it wasn't. And the implication of that constancy, of course, led to special relativity, led to the fact that if the speed of light was a measured absolute constant in these situations, that something had to be changing because the Earth was in motion. And the answer is objects shrink in the direction of their motion, and time slows down as the motion gets faster. These are the twin, and mass also increases with the speed of an object. Those are the three effects of special relativity. And the first two of those three are essentially what is required to make the speed of light constant with respect to any observation of light arriving or leaving, or light arriving from a star that's moving away from you or towards you. These experiments have been done many, many times since then. The answer is always the same. So it's a very strong observation that the speed of light doesn't depend on relative motion. Einstein built it into a foundation of his theory of special relativity. So he sort of did a judo move on this rather strange result and said, no, this is a principle, this must be a principle of nature. And if I accept that as a premise for my theory, special relativity, here are the consequences. Mass is supple, space is supple, and time are supple. They're all supple to maintain the constancy of the speed of light. Quite an amazing theory, in fact.
Next question is from Fotis, who is on with us live. I would like to ask, what is stopping us from concluding that organic molecules found in dried up Martian mud in the Gale crater have a biological origin?
What is stopping us is the fact that the instruments being deployed in these experiments are not sophisticated enough to do life detection. They're just sort of molecular mass and structure measuring machines. And they're very primitive in their measurement of molecular structure. They're really just mass spectrometers. So they're measuring the masses of all the molecules in a complex organic sample. And that gives you, of course, the composition of it, the chemical composition. So these organic residues in Gale Crater and undoubtedly elsewhere on Mars are certainly suggestive of biological material, but they don't constitute biological material. The successor to the Curiosity rover, the Mars 2020 rover, which if you've been watching the news, you'll see has been delayed, unfortunately. And of course, with Mars, if you miss a launch window, you have to wait 16 months or so, almost 2 years. So the Mars 2020 rover is delayed until 2022. And that rover, the successor to Curiosity, and in hardware terms of the rover itself, a twin of Curiosity, but in terms of the instrumentation, not a twin, that rover does have the ability to look for nucleic acids, to look for the underlying structure of something like RNA or DNA. And so that rover will have the possibility to look at rocks and soil samples and make a much stronger inference of biological material. But at the moment, we don't have that evidence.
Thank you, Chris. The next question is from Gary Parker. You were talking about sunlight and shadow. Is it true that where the Terminator crosses the moon, the difference in temperature is 400 degrees Celsius and the lunar dust is suspended above the surface?
Yes, that does seem to be the case. I mean, the temperature thing is a simple calculation because when you don't have an atmosphere, it's just the difference in the radiative heating of sunlight versus no sunlight. And if you're in the no sunlight regime, you're getting pretty close to absolute zero temperature. And if you're in the sunlight regime, it just depends on the number of watts per square meter, which at the moon's distance, of course, is very similar to the Earth, 1400 watts per square meter, and that gives you a temperature. So yes, a dramatic temperature difference, light to dark, on any moonless body, any asteroid, any moon, Mercury, of course. And indeed, that does cause this sort of suspension of dust particles in just hovering above the surface.
All right. I think this will have to be our final question for today.
I mean, what time? We can go a little longer if there are a few.
Okay,
more.
that's fine. I just wanted to make sure that you had that time available. Okay, so then we'll just keep going. So Cristiano, who's on with us live, would like to know, what do you think about different explanations for the effects that are now ascribed to dark matter, such as attempts to modify gravitational theory?
So the main alternative to a dark matter particle, because at this point, dark matter, if it exists, has to be a subatomic fundamental particle, are a series of a sort of related set of theories called MOND, which is an acronym, MOND, standing for Modified Orbital Newtonian Dynamics. And so MOND essentially takes Newton's law of gravity, an inverse square law, with the force declining as the inverse square of the distance from an object, and alters those dynamics, changes the force law essentially. So if you flatten out the force law slightly, you can actually, with a modified version of Newton's force law, you can actually do away with the need for dark matter entirely. It's quite actually a subtle effect in the exponent, not much of a change at all, just a small fraction. The question becomes, how can you do that with a sensible physical theory? And that's what most of the debate has been about. It's not about whether if you mess with Newton's theory, you can't explain away dark matter. The question is that a natural thing to do? And is that a reasonable thing to do? So a lot of work has gone on in this because these MOND theories have pretty much successfully explained the rotation curves of galaxies, the lensing experiments we see. I mean, they've explained or accounted for some of the phenomena of astrophysics that dark matter was invoked to explain, but they have not proved to be natural physical theories. And there's been a fair amount of work in the last 5 years to show that the MOND theories people have been thinking about and working with have a great trouble being sensible physical theories in other ways. An inverse square law, pure inverse square law, is a particularly important thing in basic physics. This is almost first and second year physics. It's called a conservative law. For instance, if you're talking about dynamics, force, and energy, it prevents you from having a perpetual motion machine. So inverse square laws of force are actually directly related to conservation of energy and momentum, which are foundational physical principles. So when you alter those physical laws, you actually mess up a lot of physics. And people have tried to kludge that or trying to, make it work somehow. But it's not very natural, and a lot of physicists just don't think it works at all. So at the moment, Mond theories are, I would say, generally out of favor. They have a few adherents, and there's a vocal subcommunity that's still working on them. But the hunt is really on for the dark matter particle. That's still the best bet on what dark matter is.
Thank you, Chris. The next question is from Rajarshi, who's on with us live, who would like to know if you can talk about when you think we might reach the stage where we are an advanced type 1 civilization ready to leave the planet and starting on living on or towards other planets.
So the question refers to a categorization of civilizations, of intelligent civilizations, done by Nicholas Kardashev, who was a Russian astrophysicist, a very famous Russian astrophysicist, did most of his work. I think the Kardashev classification of civilizations goes back to the mid-1960s. I may be wrong on that, but I think it goes back that far. Kardashev was a collaborator with Carl Sagan. They wrote a very sort of foundational book on intelligent life in the universe in the early 70s, I think. So Kardashev was one of these visionary Russian scientists. There were a number in astronomy in the second half of the 20th century who had very, forward-looking ideas. And he was jumping ahead of the fact that we haven't detected life anywhere else, let alone intelligent life, to speculate about type 1, 2, and 3 civilizations. A type 1 civilization, that's a good place to start, because that's a civilization that can harness the energy of its star entirely. To put that in perspective, we on the Earth intercept, the Earth's surface intercepts about 1/1000th of the sun's radiation, and we utilize that radiation, extremely inefficiently, of course, because we don't even use solar energy for the most part. We use fossil fuels. So our utilization of the sun's energy is probably down at about 1 part in a trillion. So to be a type 1 civilization, so that makes us a type 0.1 civilization or something. We're close to 0 on that. Type 1 would get the whole sun's energy. The way to do that is a Dyson sphere. That's a reference that's very timely because Freeman Dyson died, sadly, but at the age of 96. He had a good long life as a physicist. Freeman Dyson invoked the idea of a civilization who could occupy space close enough to their star to construct an energy trapping dome around it that would, now it can't be a physical solid structure because that's not dynamically stable, it would break apart, but you can figure out ways to trap solar energy close to a star. And if you got all the star's radiation and then redeployed it to your civilization, you'd be type 1 star. And it goes up the classification types. Type 3, I think, is a civilization that harnesses the energy of an entire galaxy, which is an almost inconceivable amount of energy because that's a few hundred billion stars, so it's a few 100 billion times more energy consumption or usage than a type 1 civilization, and we're a factor of hundreds of billions lower than that. So these are kind of crazy concepts, really. And you might even be a skeptic and say, well, this whole idea of energy utilization and usage and scaling it up is maybe a bit naive or it's a bit old-fashioned because surely an advanced civilization would be extremely efficient in their energy use and would be parsimonious and would not use much energy at all to do the very amazing things they did with their technology. And I think there's a case that could be made for that. But it was a very influential idea. So the idea of Kardashev civilization still exists. There are papers written about it, every year, and it's an interesting idea.
All right, the next question is from Agnimitra, who is on with us live, who apparently read a paper that before billions of years or billions of years ago, there were negligible dark matter. So it's possible that dark matter is being created somehow and causing acceleration and expansion. Can you talk about that possibility? Have you heard of that idea, and can you talk about that possibility?
I think this is not the conventional. It's not really a mainstream idea that dark matter has ebbed and flow over time. The conventional part of the framing of dark matter is that the dark matter has always been there, that it's a stable subatomic particle, and so it really hasn't changed. All that's happened is it's been diluted in space as the universe has expanded. It, of course, within that expanding universe has clustered due to gravity, and so all the galaxies, the visible things we see made up of stars and gas and dust, are embedded in diffuse but still localized dark matter halos. So the question sort of comes down to whether the dark matter particle, assuming it's a fundamental particle, is stable or not, long-term stable or decays. And at the moment, I think the betting is that it's a stable fundamental particle, because otherwise we can't really explain the expansion history of the universe. Because it's clear that the expansion history was dominated by dark matter in the past. So if anything happened a couple of billion years ago, then it becomes very hard to explain why for the first 7 or 8 billion years of the cosmic expansion, the universe was decelerating due to the presence of dark matter before dark energy took over in the last 3 or 4 or 5 billion years. So I think the evidence of cosmology sort of goes against this idea of an unstable dark matter component of the universe. However, until physicists essentially have been able to detect the dark matter particle and understand its true fundamental properties as a particle, we don't really know the answer to the question.
Okay, the next question is from Edries, who is on with us live, who would like to know, do singularities really exist inside a black hole? Like, is it a real physical object, or is it just a theoretical model?
I think it's more correct to call it a theoretical model or a construct or a concept. Because first of all, it's not physical. A singularity is, by definition, a zero-dimensional entity. And that, of course, has no meaning. Because anything that has physical properties like mass or charge or anything that exists in no dimension or zero dimension or zero length unit has an infinite mass density or an infinite charge density. And so the singularity of a black hole, hypothesized in the theory, is a point of infinite mass density, and that's not physical. So almost by definition, a singularity is not a physical object because we can't understand that physically. And in fact, that is the reason why Stephen Hawking said that black holes contain the seeds of their own demise. That was a nice little aphorism he had, one of the many clever things he said about black holes. And what he meant, of course, was that it was the theory of general relativity and his application of that theory that said, yes, there's an event horizon, and yes, at the center there should be a singularity. And he knew that the singularity was unphysical and that it couldn't be the final explanation of what's going on inside a black hole. That's a whole apart from the fact that we can't observe it in principle because of the event horizon and never have observed one. So it's essentially unobservable. So when you have something that's both unobservable and unphysical, it's probably fair to say that it is just a theoretical construct.
Okay, the next one is from Cape of Good Funk, which I love as a screen name. I live in South Africa, and the SKA, Square Kilometer Array project, is, of course, a very exciting development. Can you talk about the role you think it will play in global radio astronomy?
Yeah, absolutely. We had a little tour group out of the university that we had a cosmic origins tour of South Africa and Namibia. That was a lot of fun, and we visited the SKA site in the Meerkat Array. So the Square Kilometer Array is the next great radio astronomy project. It's an interferometer, like the Very Large Array in the United States, but it is destined to be 100 times more sensitive than any radio interferometer that came before it. So any project that moves the state of the art forward by a factor of 100 is pretty impressive. And the Square Kilometer Array is truly impressive. when they were going to locate the square kilometer array, which of course is not one telescope, it's not even a couple of hundred, it's a couple of thousand telescopes. There's a large distributed array that's spread over thousands of kilometers, and then at the center there's a close packed array of smaller telescopes, hundreds of smaller telescopes separated by tens or hundreds of meters. And that's how you get all the different spacings that let you make a beautifully accurate radio map. When the site was being competed worldwide, because it was a huge prize, a multi-billion-dollar project that was going to benefit whatever country got the project, the two finalists in the competition were Australia, which has a very strong tradition of radio astronomy going back to the Second War. They were one of the founding countries of radio astronomy, and South Africa, which has a long history of optical astronomy going back 150 years, and a decent history of radio astronomy too. And whether it was a fudge or just a sort of cop-out, however you want to view it, they ended up sharing the prize and said, okay, we'll build this thing in both countries on both continents and use the baselines between the continents to get the most accurate scales of resolution in the interferometer. But it's a huge project for South Africa. It's, again, multi-billion dollars going to each country over a period of 10 years. And at the moment, we're just seeing the prototype radio telescopes being deployed, and they're doing science, they're doing astronomy already, even though they're not at the level of the full final square kilometer array. It's very exciting. It's helping South Africa build its infrastructure to train new generations of astronomers and engineers, because radio astronomy, you know, in large part is electrical engineering, and there's a lot of mechanical engineering involved too. So these kind of science projects are extremely good for a developing country, which South Africa still is, to improve its infrastructure and its scientific capabilities. And I could feel the excitement when we visited their site and just talked to other people in the country about what they thought about astronomy or the square kilometer array. For instance, most South Africans that I met who weren't scientists or astronomers had heard of it, so they knew about it because it was a big deal in South Africa, and so it should be.
Thank you, Chris. The next question is from Florian, who's on with us live, who says, one way to search for intelligent life is to search for stars that appear in the infrared but not in the visible light. Possibly as this may indicate a Dyson sphere or a Dyson swarm. Have we ever found, do we know of any such objects?
We don't, but it is a good way to look for intelligent civilizations or intelligent life, and I'll let me explain why. So in SETI, the search for extraterrestrial intelligence, the traditional approach was radio astronomy, is looking for pulsed, narrowband radio signals whose properties, especially their bandwidth, was too small to have arisen by a natural astrophysical process. And then to look for pulses, of course, that were telling a story somehow, like Morse code, or were encoding information, and so clearly had to arise artificially. So that's traditional SETI going back to the 1950s and Frank Drake, late 1950s, Project Ozma at West Bank. In the last 10 or 20 years, a second strand of SETI has been optical SETI, which looks for lasers light, because we now have powerful enough lasers that if we were beaming out these lasers targeted into space to another star, we could briefly, because they're pulsed in sort of trillionth of a second, we could outshine the sun. Reversing that logic, if we look at stars out there, tens, hundreds of light years away, and chop their radiation or parse the information very rapidly, every billionth of a second or so, and a civilization was beaming pulsed lasers from their planet, again, those lasers would outshine the parent star for brief intervals of time. So that becomes a second way to look for artificial pulse signals with optical method. These are both very intentional methods of SETI. They rely on a civilization to have constructed technologies, either radio transmitters or lasers, and to use those in a very particular way to communicate. There's a third mode of SETI, which the question is alluding to, called passive SETI. And passive SETI relaxes a very important assumption of intentionality and just says, well, a large an impressive technological civilization will have a lot of use of energy. They'll be using energy as we do on the Earth. And no energy using civilization is perfectly efficient. They will have leakage energy or radiation energy or heat energy, because basically you're turning ordered energy into disordered energy, which in the lowest level is heat. And so if a civilization, for example, was trapping light from their star with a Dyson sphere, it would essentially be trapping that visible light, harvesting some fraction of that energy for the use of the civilization, and then the residue would be leaked off into space as infrared radiation. So the prospect of looking for a civilization turns into looking for an infrared excess in a star that should not have infrared radiation. And that's a telltale for a civilization potentially harvesting that star's energy and then betraying their existence by its heat leakage out into space. It sounds good. I mean, it sounds great. It just turns out to be a difficult experiment to do. And it's because astrophysics is messy. It's because stars are not quite as simple objects as we might hope or imagine. Stars don't exist in pure vacuum. They're surrounded by gas and dust, and that gas and dust gets heated by the starlight and re-radiates in the infrared. And so the stellar environment becomes a contaminating infrared signal to the signal that you might be looking at. So passive SETI has one huge advantage and a couple of huge disadvantages. The huge advantage is that you don't have to make an assumption about the civilization and their intentions. It just requires the fact that a civilization uses energy, and in terms of the laws of physics, it can't do that perfectly efficiently. The disadvantage is, of course, that infrared signal, even an infrared excess, can arise in a number of different ways and a number of different reasons, and it's going to be very hard in a particular situation to be sure what it is you're looking at, because, of course, that's the only signal you get. If radio signals start beeping at you in binary code, then you're pretty sure you're looking at an intelligent signal. Just the infrared excess around a star is not a good enough telltale. So it's an experiment worth doing, but it hasn't been decisive so far, and it may not be.
Thank you, Chris.
Maybe we'll take Alexander's as the last question.
All right, sounds good.
Which is?
Shoemaker-Levy 9 crashed into Jupiter.
Yeah.
People often say that Jupiter has no surface, so what exactly did it crash into? And when we could see the burn marks on the surface, what had burned?
Right. So I was thinking about this particular thing recently because until we had to cancel our Festival of Books, which should have taken place last weekend, one of the many casualties of COVID-19, I was due to interview David Levy on a panel on the last afternoon of the book festival. David Levy's written a book, and since the question is about Shoemaker-Levy, I'll mention the book too. It's his autobiography. It's called A Night Watchman's Journey. It's nice. It's a fun book. If you're an amateur astronomer or like amateur astronomy, it's like a must-read. His life story of how he became a comet hunter, and of course Shoemaker-Levy was one of only several dozen comets that he discovered, mostly working with the Shoemakers also. He has his own private observatory in southern Arizona down near Sonoyta, and he's a very active amateur astronomer. So he and the Shoemakers, working in the US, also in Australia, identified this comet that had essentially been ripped apart by the gravity of Jupiter as it went through Jupiter's system. It had been fragmented. There's a lot of background noise. Okay. It had been ripped apart by Jupiter's gravity and turned into like a string of pearls and 12 or 14 different pieces. And its orbital dynamics were such that it was easy to project within a year of its discovery that it was going to plow into Jupiter. So this was like the opportunity of the century, essentially, because no one had ever seen this. And since people had become aware of what happens when a comet or an asteroid or a big chunk of rock and ice hits the Earth, you can get mass extinctions and you can get, huge mayhem, was pretty interesting to have a ringside seat for watching a big chunk of rock and ice hit another planet, in this case, a gas giant. But it is a gas giant. The surface of Jupiter, it's inferred by magnetometry to have an Earth-like core, probably 3 or 5 times the mass of the Earth, but you can't see it. It's through this these dense banks of clouds, thousands of kilometers deep. And yet it did make quite an impressive showing. And so as the pieces slammed into Jupiter, moving at several tens of thousands of miles per hour, there were flashes of light, there were dark patches, scars, if you like, and they persisted in Jupiter's atmosphere in a couple of cases, I think, for almost a year. So what was that all about if all it was rock plowing into gas? I mean, and the answer is that even though it was only plowing into a sort of gradually thickening gaseous atmosphere, it was doing so with enormous speed. And what was happening to those pieces of Shoemaker-Levy is that they were, as the gas got denser, as it moved through Jupiter's upper atmosphere, they were being decelerated and ablated, and enormous energy being deposited on the chunk, which was sort of evaporating it, just essentially burning it up as it would in the upper atmosphere of the Earth over a period of probably hours or maybe a day for each chunk. And that heating up, that conversion of kinetic energy into thermal energy, and then evaporating the rock and depositing that energy into the upper atmosphere of Jupiter, deposited a phenomenal amount of energy into the piece of Jupiter's atmosphere where each chunk landed. And of course, Jupiter was rotating as the chunks arrived. So the planet spun a little, and then the next chunk went into an adjacent piece of the atmosphere. So you got to see them making their mark in a range of places in Jupiter's upper atmosphere. So the scar and both the light flashes that were seen and then the darkening afterwards were the result of a phenomenal amount of energy deposition from chunks of rock, each of which may have been, I don't know, a few tens of meters across, so not huge, but the kinetic energy at that speed is phenomenal. Jupiter's upper atmosphere is, of course, pretty cold. It's far from the sun, 5 times further from the sun than the Earth. So that was spontaneously heating the atmosphere up in a really large amount, and that gas would, of course, radiate and fluoresce and do all sorts of wild things. And then when the energy dissipated and sort of moved through the atmosphere by circulation, the rapid cooling of it created a sort of darkening after effect. So you'd have a flash and then a shadow, or the appearance of a shadow. So it wasn't really a shadow. It was just a sort of the loss of all that energy leading to a place that was actually cooler than the surrounding gas. So it was pretty interesting. The planetary scientists had a lot of fun just trying to figure out how to explain what was seen, because it sure did look like they hit a surface, but of course they didn't. So thanks for that. It was a great question. And thanks to you all for persisting through the little bait and switch we pulled on you. And we'll be back with you in a couple of weeks, coronavirus permitting. Well, this is social distancing of a safe kind, so we'll be back.